So we've talked about equilibrium, we've talked about determining pH of solutions, we've talked about pH of strong acids, strong bases, weak bases. In this module, we really want to focus on determining the pH of a salt solution. We talked about salts in first semester, we're bringing it back. Remember, and I will talk about it again in just a sec. It'll be on the first slide, but remember, as a definition, a salt is something that's ionic, that when I split it apart, basically the cation portion never came from anything that had hydroxide. The anion portion came from something that never had a hydronium or proton specifically with it. So when we're looking at this, we need to be able to first determine what type of pH the salt should produce. And so we're talking about Bronsted-Lowry acids and bases in this situation. We're talking about their conjugates. So a Bronsted-Lowry acid will form a conjugate base. So its conjugate will form a base and act as a base in solution. If we have a base, it forms a conjugate acid, meaning it acts as an acid in solution. We've talked about this, we've identified the conjugate acids and bases, but we haven't really talked about what they do in solution yet. And this is the chapter, or the module we really want to focus on that. You should be able to calculate the concentrations of any dissolved ions or molecules in a solution of a weak acid or a weak base. If you're given the Ka for an acid, you should be able to tell me the Kb for its conjugate base. If you're given Kb for a base, be able to tell me Ka for its acid. You absolutely need to know this relationship. The value of Ka times the value of Kb is equal to Kw. And remember, Kw is 1.00 times 10 to the negative 14 if we are at 25 degrees C. And unless otherwise specified, we assume we are at 25 degrees C. So, acid-base properties of salt solutions. So there are two ways to define a salt. First, a salt is an ionic compound whose cation is not H+, and whose anion is not OH-. If it's an ionic compound with a cation H+, that would make it an acid. Anion OH- or hydroxide, that would make it a base. So salt is anything that we can put into solution. So, we think of things like zinc nitrate, that's a salt. Lithium chloride, that's a salt. Magnesium bromide, that's a salt. These are all salts. It's also, though, the product of an acid-base reaction, and that's the true definition of a salt. So we've talked about this previously in first semester as well, but the perfect example is if I took sodium hydroxide, dissolved it in water, and mixed it with hydrochloric acid, this is going to form water and salt. Now, we don't think much about it. We think, okay, we swapped the partners. Of course it formed water and salt. And this is what most of us think of as salt. Sodium chloride is like the base definition of salt. It's table salt. But this salt is the product of an acid-base reaction. So we can also think about them in that sense that they are products of this reaction. And so if we can look at a salt and we can figure out where it originally came from, which two components reacted to form it, we should be able to tell how the solution is going to behave. So, for example, what acid and what base formed the following salts? If I have sodium acetate, we're going to split this compound up, kind of like we did when we learned naming, where we split up the two parts. So if I split this up, I've got sodium and acetate, Na+, and acetate C2H3O2-. Sodium plus, now I'm going to think about what acid and base formed this. The kind of trick here is if you've got a proton here, not a proton, thinking about adding protons. If you've got a cation, try to add hydroxide. If you've got an anion, try to add a proton. So, NaOH, and I never remember how you guys actually write acetic acid because I don't write acetate like this, but C2H3O2H, I would write this as CH3COOH, same thing, but acetate becomes acetic acid. Sodium ion from sodium hydroxide. So the point here is what acid and base can form the following salts. Sodium acetate can be formed from sodium hydroxide and acetic acid. Now we look at it, and we're going to talk about this in a sec. How do we determine if this salt is acidic, basic, or neutral? But because this came from sodium acetate, or because this came from sodium hydroxide, and sodium acetate. Sorry, I keep saying the wrong thing. Sodium hydroxide and acetic acid is what I am trying to say. That's what I'm trying to say. Because those two things reacted, so it's like saying NaOH plus CH3COOH reacted, and they formed water and salt. Now, the thing is that sodium acetate is not actually going to stay as sodium acetate in solution, because if you remember your solubility rules, all acetates are soluble. So what's going to happen is this thing in water is actually going to form it does say aqueous, but if you want to think about, make sure you realize that's in water, it's going to form sodium ions and acetate ions, which is why I'm able to split it apart. So what I'm looking at now, what I'm trying to figure out here is how is this going to behave? Why not this? Why don't I care about the sodium? The truth is because sodium comes from sodium hydroxide. So the sodium ion here is the conjugate acid of a strong base. Now, the reason it's a strong base is it dissociates 100% in solution. Weak bases would create an equilibrium where both species are going to exist. Sodium hydroxide is a strong base. It forms entirely sodium ions and hydroxide ions. What that means is the sodium ion doesn't really want the hydroxide back. It doesn't need that. Remember, sodium, if it loses one electron, it has its noble gas configuration. Sodium ion is incredibly stable in solution. There's no reason for it to react with water to have to, A, accept a proton. Not going to happen. It's already got a positive charge. It's not going to accept another positive charge. Or B, combine with hydroxide. It is very stable. So this does not contribute to the acidity or basicity of the solution at all. It stays neutral. The acetate, however, will react with water. Acetate is the conjugate base of a weak acid. It is a base. Acetate will now go in and react with water and form a solution that's basic. So we need to be able to identify where these salts come from so we can identify if the solution will be acidic or basic. So again, if I have sodium acetate in solution that came from sodium hydroxide and acetic acid, this will be a basic solution because I'm going to have CH3COO minus in water, and it's going to form acetic acid and hydroxide. The fact that it forms, two things happen. One, it accepts a proton, which makes it a base, which makes this the acid. It also generates OH minus in solution, which is the Arrhenius definition of a base. So I know that went a little bit beyond what this slide specifically asks, but we need to be able to identify because this is what we're trying to do. We're trying to figure out how this is going to behave in solution. So let me erase this. Which acid and which base formed the following salts? This was formed by NaOH plus CH3COOH, which you may write as C2H3O2H or some form of that. The next one is ammonium cyanide. So I'm going to split this up and I see NH4 plus and CN minus. Now NH4 plus, I could put hydroxide to that and say it's ammonium hydroxide. That will work. It will work if we think about it this way. It will work if we think about the cation and hydroxide. But it's tricky because it's also got a nitrogen in it, and the nitrogen itself originally is basic. Nitrogens have a lone pair, they can accept a proton. So we could say from ammonium hydroxide, that's perfectly fine, but this could also have come from ammonia. Ammonia accepts the proton and forms this conjugate acid. It is still an acid. And the CN minus comes from cyanide. We're going to put a proton with that. So we're going to say that this comes from ammonia, NH3, plus hydrocyanic acid, HCN. A general shortcut you can follow that will get you to the right spot if you can recognize where these salts are. The salt that is formed from a strong acid reacting with a strong base is always neutral, such as sodium chloride, potassium chloride. They're both neutral in solution, always. If I have a salt, so the salt is the product of the reaction of a strong acid and strong base. The salt that's formed, the product that's formed from a strong acid and a weak base, is going to be acidic. If I have a strong acid, so HCl, weak base, ammonia, this is going to form NH4 plus and Cl minus. The reason HCl is a strong acid is because it dissociates 100% in solution. Acid strength comes from the stability of its conjugate base. This is my acid. This is my conjugate base. The base is so stable that that's what makes the acid strong. Chloride ions. A chloride ion has its noble gas configuration. It has everything it wants and it doesn't have to share. It is the most stable I can make this, and it's very stable. There is zero reason why the chloride ion would ever want to take a proton back. So that's what makes HCl so strong. That's what makes it release all its protons, because it can form that chloride ion. This is very, very stable. Therefore, chloride is not going to react with water. When the chloride does not react with the water, it keeps the water neutral, because it keeps the amount of hydronium ions and hydroxide ions that are naturally present in water equal. It makes no effect. But ammonium, so this is your base. This is called ammonia. This is your conjugate acid. We call it ammonium. Ammonia comes from a weak base. So when I put ammonium in solution, it reacts with water to reform that original weak base. It forms ammonia, and in order to do so, it must give up a proton, so it forms hydronium ions, which increase the acidity of the solution, because that is an acid. So salt of a strong acid and weak base will be acidic because it's going to create H3O plus in solution. This is going to donate a proton. It's going to act as an acid. It forms the conjugate base. Here, water is acting as a base because it's accepting the proton, and hydronium ion is its conjugate acid. The salt of a weak acid and a strong base will always be basic. So here, let's look at acetic acid again. CH3, COOH, plus NaOH, if I swap partners here, I'm going to form NaCH3, COOH, plus water. Water doesn't care. This further splits apart into sodium ions and acetate ions. Sorry, I wrote an extra H there. This should not be an extra H on the end. I apologize. There should actually be acetate, which is that. CH3COO minus. So, because it's not, remember, it's soluble. All acetates are soluble. It's not going to stay in solution. So that sodium ion we've already talked about. The sodium ion is incredibly stable. It's not going to react with the water in solution. Therefore, it keeps the solution neutral. But acetate will react with water. Specifically, it will take one of the protons, forming hydroxide. So it acts as a base. It accepts a proton, forming a conjugate acid. Water in this case acts as an acid because it donates a proton, and this is its conjugate base. It's also increasing the hydronium ion concentration in solution because it's creating more of this in solution than what water naturally has. Hence, the solution will be basic. The salt of a weak acid and a strong base is basic. And the last example here, the salt of a weak acid and a weak base is completely dependent upon the Ka of the weak acid and the Kb of the weak base. We have to calculate it. We would have to see how much that weak acid creates in solution, how much the weak base creates in solution of hydronium and hydroxide ions respectively, and then calculate where the pH was at the end. So again, anions of strong acids are such weak bases that they do not affect pH. Again, HCl, strong acid, plus water gives me Cl minus ions, plus H3O plus. Hydronium is actually the strongest acid that can exist in an aqueous solution. That used to throw me off because I used to think, but solutions have different acidity. That is correct. Solutions have different acidity because adding a stronger acid creates more hydronium ions in solution. The more hydronium ions I have, the stronger the acid the solution, or stronger acidity the solution has, the lower pH it has, the more acidic it is. But H3O plus is actually the strongest acid that will exist in aqueous solution. But again, this anions of strong acids, this is such a weak base. Remember, bases want protons. This doesn't. Chloride ion does not want a proton. It is very stable by itself. This is why they don't affect pH. HCl, HNO3, HLO4 are 3 of your strong acids. You have 7. But therefore, chloride ion, nitrate ion, and perchlorate ion do not affect the pH, and these are always spectator ions in an acid-base reaction. Again, you do have 4 other strong acids that you should know. So you've got sulfuric, you've got chloric acid, you've got hydrobromic acid and hydroiodic acid, and they do the same thing. Their conjugate base is a great spectator ion, but that's all it is. When I look at strong bases, I see the same thing, just, in this case, it's the conjugate acid that's so stable. Cations of strong bases are not acidic at all. They do not affect pH. And that's why we're talking about like sodium hydroxide. We could also talk about KOH. Any of your strong bases. Put this into water. Sorry. Actually, I don't even need to put it into water. I keep forgetting I need to do that for weak bases, but not for this. This splits up into K plus OH minus. We're talking about this specifically at that point. So this doesn't care. It has no reason to ever want that hydroxide ion back. It's got what it wanted. It gave away its electron. It is such a weak conjugate acid that is not acidic at all. It will not affect pH. NaOH, KOH, calcium hydroxide, you have 8 overall. Remember, you can read these right off the table. They're all grouped together. But these cations here are conjugate acids, but they don't affect the pH, and they're always spectator ions in your acid-base reactions. So let's work some calculations. What is the pH of a 1 molar NaCl solution? The shortcut to this is to think about, where did NaCl come from? NaCl, Na plus, Cl minus, NaOH, and HCl. Again, I always add hydroxide to the cations. I always add a proton to an anion. And then I look at them and say, what do these look like? This is a strong base. This is a strong acid. So shortcut is that NaCl is a salt of sodium hydroxide and HCl, which means it is neutral. And the pH is 7. If I have NaCl, I know this is a strong electrolyte because it's completely soluble in solution. It forms sodium ions. This is a spectator ion because, again, it comes from a strong base plus chloride ions, which is also a strong spectator ion because it came from a strong acid. I have absolutely asked questions like this on exams before, and students have tried to calculate the pH and then given me really wonky numbers if it's a multiple choice question. If you see the salt of a strong acid plus a strong base, please tell me it's the pH of 7. Please don't waste your time. It is pH of 7. The other trick to this is that in this question, now on homework you can't do this, but on assessments you could. I did not give you a Ka or Kb value because it doesn't have one. It went to completion. It's not forming equilibrium. The absence of a Ka or Kb value suggests to me that it is a strong electrolyte, that it is completely neutral, and it came from a strong acid, strong base. Be careful with that on homework because, of course, you can always look up the K values. But, okay, so which K value do you use? Do you use Ka or Kb? The truth is it depends on how it's acting. If an ion is acting like a base, you have to use Kb. Acting like a base means forming hydroxide in solution. So forming hydroxide means it's a product. If the anion is acting like an acid, meaning forming hydronium ions, meaning that is a product, you need to use Ka. And Kw is equal to Ka times Kb is equal to 1 times 10 to the negative 14th at 25 degrees C. But unless I specify, you can assume that this relationship is valid. If I needed a different temperature, I would have to give you that Kw value. This is the only one I expect you to memorize. So conjugate acid and bases. Again, the conjugate acid of a weak base, acidic. Conjugate base of weak acid depends on the relative strengths. You can look at this table and kind of see, how it's going to behave. It is, if you're looking at the cation, it is the conjugate acid of a weak base. Conjugate base of a strong acid is acidic. Conjugate base of weak acid depends on the strength. So look through this table. It's a nice little summary slide. The conjugate bases of weak acids are weak bases, and they are basic enough to affect your pH. HCN, hydrocyanic acid. CH3COOH, acetic acid. HF, hydrofluoric acid. These are all weak acids. Therefore, their conjugate bases do affect pH. If I have a solution that has cyanide, acetate, or fluoride, notice those are the ionic forms. Those are ions, not elements. I did not just name the elements. Then the solutions themselves will be basic. If they are by themselves, or if they're with a spectator ion. So if I had like potassium fluoride or lithium acetate, I expect the pH to be basic. If it's mixed with an acid, a weak acid, like a salt from a weak base, then like ammonium, it depends on the solution. So expect these to contribute base. So expect the pH of these to be increasing. And the conjugate acids of weak bases are acidic enough to affect pH. So one thing to look out for is a nitrogen atom with a positive charge. Nitrogens with positive charge. Nitrogens form amines. Remember amines from first semester? And if I form it with a positive charge, that's where how I go from ammonia to ammonium. This is absolutely acidic. So let's work a couple examples. What is the pH of a 1 molar NaF solution? And I clearly did not give myself enough space here. So we're going to have to take over the slide. And then, because I forgot that I had this set up to put on a whiteboard and not on a video. So 1 second. We're looking for the pH of a 1 molar NaF solution. It does give me the Ka of HF. Couple things to look out for when you're doing these problems that kind of always clued me into what I need to be doing. First, it does tell me 1 molar NaF, but I know NaF is a strong electrolyte because I know anything with sodium in it is a strong electrolyte. So I know NaF in solution is going to form sodium ions plus fluoride ions. I then look at my two pieces here and I say, okay, well, it told me I started with a 1 molar sodium fluoride solution, which means that I have 1 molar sodium ions floating around and 1 molar fluoride ions floating around. This is a strong electrolyte, so it's split apart entirely. And that's how I know I have 1 molar sodium ions, 1 molar fluoride ions. Now I'm going to look at sodium fluoride. Sodium, if I pair that up with hydroxide, is sodium hydroxide. That is a strong base, which means this is a spectator ion. Which means I'm going to ignore it because it is not going to contribute any hydronium or hydroxide ions. It's not going to cause any water molecules to form hydronium or hydroxide ions in solution. So it's going to be complete spectator. It's not going to affect my pH. But F minus, if I give that a proton, it becomes HF. I know hydrofluoric acid is a weak acid, which means this is a conjugate base of a weak acid. So right now, I expect this solution to now be basic. I'm going to take that F minus and put it into water. If F minus reacts with water, it is a weak base, so it is going to grab 1 proton from that water and form hydroxide. So yes, it is behaving as a base. It accepted a proton and it formed hydroxide. I do need an ice table because it is a weak base. And I know that I have 1 molar F minus to start. Water doesn't factor into the ice tables. I don't have any HF at the start, and I have approximately no hydroxide at the start. Why approximately? Because I know with just water in solution, I actually have 10 to the minus 7th hydroxide ions floating around. But I know that the F minus is going to produce more OH minus ions in solution, causing the pH to increase. Change, minus X, and at equilibrium, I have 1 minus X, and X. Now, it gave me the Ka, but I need the Kb. How do I know I need the Kb? Because I'm forming hydroxide. When hydroxide is in my K expression, I need Kb. So if I wrote out my Kb expression, which is always good practice to do, I see that I have OH minus in my numerator, which means I have to have Kb. In order to get to Kb, I'm going to have to rearrange. Kb is going to be equal to Kw divided by Ka. So 1.00 times 10 to the minus 14 divided by that Ka value of 3.53 times 10 to the minus 4. This gives me a value of 2.83 times 10 to the minus 11. Do I expect it to be that small? Yeah, the Ka value is kind of large, so I actually do expect it to be kind of small. I don't expect a lot of the F minus to be forming. So this is equal to 2.83 times 10 to the minus 11. Let's go ahead and move up here. In simplified, plug in what we know from our table, x squared divided by 1.0 minus x, but as I've told you guys, we're going to assume that x is really, small compared to our Ka value, and we see here it is. Our Ka value is so small, we've said before that if Ka is less than 10 to the negative fifth, we can probably ignore it, that minus x. Ka is incredibly small, so we're going to go ahead and ignore that and say equals 2.83 times 10 to the minus 11. Solve for x, we get an x value of 5.3 times 10 to the minus 6. And remember, that equals your hydroxide concentration at equilibrium, because what we solved for was x. You could also plug it back in and say, okay, if I actually took 1 minus x here, would that x have mattered? No, it's so small, it really didn't matter that we ignored it. Now I'm going to take the log of that to find pOH. And I find my pOH value to be 5.27. I know that 14 minus pOH is going to give me my pH, and I find my pH of my solution to be 8.73. So I've solved this through, and I get a pH of 8.73. Then I stop and I say, does that make sense? Does pH of 8.73 make sense? Well, I'm using a sodium fluoride solution. Sodium fluoride is going to automatically split up into sodium ions and fluoride ions. Sodium comes from a strong base. Yep, that's not going to do anything. It's going to be a spectator. The fluoride, though, comes from hydrofluoric acid, a weak acid. So fluoride itself is a weak base. I have now determined that the pH of the solution will be basic. Not strong, but a base. So yes, my answer is correct, and I move on to the next question. But notice all the things we had to recognize here. We had to recognize that sodium fluoride split up entirely in solution, that sodium fluoride was a strong electrolyte, that the sodium ion itself was a spectator, the fluoride ion was a conjugate base of a weak acid, that we needed a Kb value, that we're producing hydroxide, so therefore that X is actually determining the amount of hydroxide we produce in solution, that we then find pOH, and we can then calculate to pH. So there's lots of steps in this process that you need to be careful of so you don't mess them up. Let's go ahead and erase all this and work on the other example. So what is the pH of a 1 molar NH4Cl solution? Now it's probably a good guess that that solution is going to be acidic just because we just did one that was basic, and I'm going to flip things around on you guys, but what if you're on an assessment? You wouldn't know that. You wouldn't have that little clue. So let's look at this. Shortcut here. NH4Cl is the salt of a strong acid, HCl, and a weak base. Ammonia. Therefore, the pH is going to be less than 7. I've got NH4Cl. NH4Cl splits up in solution to form ammonium ions and chloride ions. It tells me I have a 0.10 molar solution. This is a strong electrolyte, which means I will also have 0.1 molar ammonium and 0.1 molar chloride ions. Chloride is the conjugate base of a strong acid, so this is a spectator. Ammonium is the conjugate acid of a weak base, so will further react with water. So if I have, and again, when I put that in solution, that's immediately going to split up, so I'm automatically going to have these ammonium ions floating around. They are going to react with water, and they're going to donate a proton to water. By donating a proton, they're behaving as an acid, and they're forming hydronium ion. I originally had 0.1 molar NH4 and no ammonia And we see approximately no H3O plus because, again, the original concentration of H3O plus was 10 to the minus 7th. Change minus x plus x plus x, and at equilibrium, 0.10 minus x, and x. Now, go ahead and set up your K expression. And because I am forming ammonia, but also hydronium ions, I need to have a Ka expression because, again, A is hydronium. If I was forming hydroxide, I have Kb. NH4 plus. What does this equal? Well, now I need to know Ka, and it gave me Kb. That's usually what happens for salt solutions. So I'm going to do that up here quick. Ka is equal to Kw divided by Kb. 1.00 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5th gives me 5.56 times 10 to the minus 10th. So this equals 5.56 times 10 to the minus 10th. And I'm going to go ahead and move this up here and plug in what we know. My ammonia and hydronium ions are both being represented by x at equilibrium. So I've got x squared divided by 0.10. Again, I'm going to ignore that minus x. I'm going to assume my Ka value is really small. So I should be able to assume that x is really small as compared to that 0.1. This equals 5.56 times 10 to the minus 10. Solve for x, and I get 7.5 times 10 to the minus 6th. And this time, this equals my hydronium concentration. Because again, x represents concentration of this species at equilibrium. Go ahead and take the negative log. 7.5 times 10 to the minus 6th. This equals my pH. And I find the pH of the solution to be 5.13. So I've solved it through, and I found that yes, in fact, my pH did stay acidic as expected. I didn't realize that was the end of this module, obviously. But go ahead and practice that. So kind of keys to these things, like some of the tricks to these, is recognizing that, so the way I like to break things down in math, it makes more sense to me, but now I can see what's happening in solution. But, you know, if I'm told NaF and I see HF, that means it's a salt. I'm seeing this is HF, this is NaF, that's going to split up into Na plus and F minus. I'm given a Ka value. I'm not giving any values for the sodium, so it's probably a spectator. It is a spectator, but I still need to guarantee that. I still need to think in my head, how does sodium react? Would sodium actually want to form? You know, it would come from sodium hydroxide. That's a strong base, so I would ignore it. I also see HF here, though, and this is F minus. This is the conjugate. I know HF is an acid because it can donate a proton, so this is probably a base. I know this is giving me Ka, but this is a salt. I probably need Kb. Those are the kind of things that I think about that can help me get these problems correct.